brain, and he can be a conduit to Dan. So Nick Dietrich is going to wow us with a presentation on specifying the upper atmosphere through data assimilation of radio occultation observations. There we go.
Awesome. Thank you. Yeah, so today I just want to highlight some of my PhD research where really I'm just focused on using radio occultation observations because they are kind of the most, some of the most abundant three-dimensional low latency observations we have of the upper atmosphere, and really focusing on leveraging them for both neutral and plasma state specification. So I don't think I need to go over kind of upper atmosphere background, but kind of want to highlight and build upon what Dan Hodis said, is that we can also kind of think about the upper atmosphere as really, it is dependent on initial conditions and external forcings, kind of depending on what you look at and kind of the time scales you're interested in. Where really for external forcing, kind of the main ways we use to generate our ensembles and introduce variability into the model is really from lower atmospheric forcings, solar radiance, and then also during geomagnetic storm times has additional variability. And so so what I'm working on with this project that I'm going to show you today is really kind of focusing on more of initial conditions and state specification purposes, and kind of just using external forcing just to produce our model spread and background covariances. And so the observations I'm leveraging are radio occultation observations, specifically the electron density profiles, which give a three-dimensional view of the ionosphere. They are kind of with GNSS signal coverage, we can in theory get full latitude, local time coverage of these observations, and they're already built in low latency. We do have the issue of Abel inversion, introducing biases and errors within our observations. And you kind of just get maybe around this by just assimilating DEC, but for the purpose of neutral specification, I think kind of using this profile information can be a valuable asset. So kind of I'll go through two different sections where I'm using RO EDPs to kind of assess them for two different purposes. The first being plasma state specification. And I'll do this in just a comprehensive OSSI approach, really more so to guide and inform future mission planning of RO missions. And then second part, using strongly coupled data assimilation approaches, using a coupled IT model and with background covariance structures to actually inform what the neutral states are looking like, and kind of enable global specification. Really, I'm focusing on estimating neutral density for purposes of satellite drag estimation. And for that, I'll be doing with the OSSI and OSE, or a reanalysis kind of approach. So first, for plasma specification, we looked at just a very popular study, 2013 St. Patrick's Day storm event, where we used a comprehensive OSSI approach. We used a different truth model and experiment model where we're retrieving our observations from WAM-IPE and then assimilate them into TIGCM, generating our ensembles. And then the other comprehensive part of this is that we're doing a full Abel inversion of our EDP observations so that we kind of are systematically accounting for the real errors within these EDPs. I also want to note, since this is a JEDI conference, I'm using Dart for all of this, so it's just the EAKF implementation. And I'm only updating plasma states here. So here is just an overview of the hypothetical constellations we looked at, kind of more based off what Cosmic 1 and Cosmic 2 look like. They have different altitudes and different orbital inclinations. You can kind of see here just the different latitude coverages they have based on their inclination. And there's 4 different constellations that we looked at, and I'll just kind of relatively assess for how well they specify the ionosphere. And then I also have this handy kind of notation up here of first number is the altitude and the second number is the inclination. So because this is an OSSI, we can also do pretty complete enough uncertainty or error quantification of our EDPs. where here is just we're comparing against what WAM-IP produces versus what the able inversion retrieval is. On the left, I have just a grid of the NMF2 and HMF2 errors, where we see pretty good as kind of supported of what we see with real cosmic observations. Where really this HMF2 is very well retrieved with these observations. And on the right, this is an altitude profile of the error fraction, where kind of if we go for really low altitudes, we get pretty bad errors. But then as we go up in higher altitudes, kind of more in the F region, the retrieval is very good. And I also want to note that this is very local time dependent of what these errors that we see. And then I'm using these errors that we quantify actually in the observation R matrix as well. And so just comparing kind of the WAM-IPE with cosmic or retrieved RO EDPs, I'm showing two altitudes. Where I'm first going to focus on this 400-kilometer altitude comparison, where you can kind of read this observation chart as the first column are observations, the second column is our TA EGCM prior, and then the third column is the posterior of after our assimilation. Right, then I'm showing IP on the y-axis. And then I also split this between latitude. So you can kind of see for 400 kilometers, pretty much the posterior is consistently improving in our estimation. And then also these able retrieved errors are very good and very accurate. But when you go to 200 kilometers, you can kind of see just the biases really take place in the breakdowns in the spherical symmetry assumption that we use for able inversion really manifest. But I do want to note that it's really just this low latitude region here where we see worsening performance with this assimilation. The mid and high latitudes don't look great, but there are still some benefits that we're getting out of this assimilation in these regions. And it's kind of the purpose, kind of the outcome we got out of this was kind of just be more careful during these low latitudes, low altitudes regions where we have these really long radio passes, and then the electron density can be very low beneath the EIA structures. And then secondly, kind of results from this work is because we had so many observations available to us and a lot of OSSIs that we could pull from, kind of motivated by what the lower troposphere is doing with ROMEX, we can kind of look into potentially a limit in performance of, at some point we had a cap in performance and plateauing where assembling more observations isn't really gonna maybe not improve performance. And this is just kind of just defined using a OSSI fractional improvement. So our OSSI improvement over no assimilation control versus the Allery observation counts we have. And then this is split between latitudes. So you can kind of see for low and mid latitudes, we kind of start to see a plateauing performance. Or for high latitudes, we kind of don't have enough observations to kind of really definitively say where this would be. Kind of requires further investigation. And then also, I just want to note that this cap could be real, could not be real. There's a lot of different data assimilation kind of filter pieces and observation errors that are all contributing to this and kind of requires a lot more work to kind of look into. So next, I want to jump into the neutral specification. And so with this, I'm really focused on using this RO observations and through a strongly coupled data assimilation framework, I hope to use it to leverage it to capture neutral density variability. And I want to kind of apply this during a storm time when kind of for conjunction analysis and orbit position errors is kind of the most, is very relevant. So with this, I just want to quickly highlight some OSSI results from a previously published paper where we synthetically retrieved EDPs from a nature run and then assimilated into Dart TAGCM. And so we kind of use these plasmas to, with different state vectors, including temperature and neutral winds, to see how well they estimate these neutral states, and then what kind of impacts they had on neutral density biases, and then also on corresponding to satellite drag or orbit positions errors. And kind of, I don't have the orbit position errors here, but you can kind of see the neutral density biases improvement in this bottom left plot. Where here, this is the first 3 hours of the assimilation. In the bottom is the experiment bias when we're updating neutral temperature compared with the no assimilation control. And we can see the improvement in these biases after about 3 hours, and then kind of plateauing after 12 hours, where we kind of we're using kind of synthetic Cosmic 1 observations, so we have full latitude coverage, and we're getting pretty much global neutral density specification. And so, so that's all nice. This is nice simulation results. So let's actually apply it to a real storm event using real observations and kind of see what comes out of it. And so with this, we chose a storm event, just a kind of a not really noteworthy storm event in 2022, but it's just nice that it's kind of, if you see the DST and KP indices down in the bottom, it's kind of has this nice 2-day quiet period, and then a sharp drop in DST and peak in KP, and then kind of back to quiet period. So a nice isolated storm event we could look at. And for this, since 2022, we'll be assimilating Cosmic 2 electron density profiles, where we do have way more observations in Cosmic 1, but they are limited to only the mid and low latitude coverage. And then for this, I want to note that our updated state vector is going to be these plasma states, and really the important one is going to be this neutral temperature, which is a very critical parameter for describing the upper atmosphere. And so kind of with this effort with doing an OSC, there was a lot of effort kind of invested into actually just ensemble initialization and filter configuration tuning to see kind of improved performance. We're really kind of, when we're working with these upper atmosphere models, they can have very large biases that we have to correct and tune to really improve our model bias or model observation biases and actually get positive impact from our observations. So you can kind of really see the effort, the results of this effort in this top right plot, where I'm showing the just the rejection rates of our assimilation. So we kind of started where if our observations are some outlier threshold away from our model ensemble, then we're just not going to assimilate that observation. So you kind of see this black curve is our initial control. So really low altitudes, we have really like 50% rejection rates, but it kind of does improve, maybe 20% up to high altitudes. And then I believe kind of this red curve is our first assimilation results, where you can see 50% of the observations are being rejected. So not great. And so kind of with this, we focused on ensemble initialization approaches. So we're perturbing geometric forcing with Weimer solar wind parameters, F10.7 index, which is just a very strong tuning parameter. Some lower boundary tide perturbations, though I want to note that TIE-GCM uses a lower boundary parameterization. So it's not fully coupled with the lower atmosphere. And then we also tested some internal parameters, such as the collision frequency between O and O+. And so at least with the control window simulation run, we kind of get this black and light blue curve as our best performing experiments, where we get really like pretty much near zero rejection at high altitudes, and then still low altitudes is a problem. And then I also want to note the filter configuration. We're doing quality control, localization, and outlier control tunings for all this as well. And so if we're looking at the O-B RMSEs, or for the forecast plasma, we kind of compare this black and this gray are kind of our two kind of control runs that we're comparing against. And then with forecasts, we're getting the best performance in these light blue curves. We're really you can really see during this peak storm time, the improvement in the forecast plasma that we're getting. And so this is more of a verification. Now I would kind of want to more focus on what this means for the real purpose of this is for neutral density specification. So during this time period, Grace Fallen is the best information we have of what the neutral density looks like. I want to note that Grace Fallen is sampling dawn and dusk local times of this period. Where you can kind of see here, this is from for the dawn side, where time is going to the left, and then the storm period starts about like right here. And you see all the initial enhancement structures, and then the subsequent cooling. And so you can see what the TIE-GCM control here. You can see the bias between models, and then the reanalysis that we're comparing to is in the bottom, where we're during this these enhancement structures really not getting as good a benefit as we want. But it's really kind of in these reanalysis results, it's really this subsequent cooling phase that we're actually getting really good performance and much better agreement with our observations. And so to be a bit more quantitative with this, this is just a orbital average neutral density of the storm time where we have the storm peak. Storm began here at hour 12 and then peak around here. And then in dark blue is our control run, and then our light blue is the reanalysis results, where we can see these reanalysis better agreeing with our GRACE follow-on observations. Just a simple bias improvement metric is down here, where just simply positive is we have improvement of a reanalysis over control compared with observations, where this is a pristine quiet period, we get some benefits. During this peak storm time, this is really kind of mixed results we're getting, because I really see this as more of probably a driver issue of like geomagnetic forcing that we're using. And then it's really in this subsequent cooling period, we're getting consistent great improvements in our observations. And then here again, this is just a comparison of GRACE follow-on with our reanalysis and control, and you can see much better agreements in our reanalysis. Kind of last note on this is because we get the most effective assimilation during this cooling response, we looked into what's happening in observations for cooling. Really kind of the thinking behind this is that it's very much more of an internally driven process where NO cooling is a very dominant, where it's emitting infrared wavelengths at kind of more low 120, 130 kilometers altitude. And so we can look at, because Time Saber has NO observations, we can actually compare what TI-UGCM has with the Saber. And so here is the split Time Saber observation split by local time. This is the fully integrated vertical flux. And then this bottom, you can see this is just the bias between these two observation and model, where I do want to know that TI-UGCM is doing actually a fine job of capturing this NO, but it's really kind of this late stage, kind of in the cooling phase, peaks that we see in Time Saber aren't really present in TI-UGCM. And then lastly, I do want to note that if we fit just a simple exponential recovery of the neutral density recovery, this is the fitted time scale, so we are in the reanalysis improving it by about an hour in error. So to wrap up, we are leveraging RO EDPs for both neutral and plasma specification. Where for plasma specification, we show kind of incomprehensive OSI approaches, hopefully information for better constellation design and coverage in order to get optimal performance. And then we can also with the OSI better characterize these able inversion errors in regions where they have negative impact, and also highlight the positive impacts as well. And for neutral specification, we have demonstrated the ability to use these ROEDPs to improve atmospheric drag errors and orbit position errors, and then also produce a reanalysis of this event that can improve these biases and the storm recovery. But also, I just want to note that there's still like way more work, and a lot of us uncover with this of limitations of our models that we really need to improve in biases and how to actually ingest variability into our models to actually improve observation agreements and get more realistic background covariance structures that are used in this strongly coupled data assimilation approach are so critical. And with that, I'll take any questions.
I have a question.
Yeah,
What else
sure.
does? So you, in your, I guess, last slide of the results, did you compare with Saber when you do the assimilation? Does it make any impact, or because the cooling is too low?
I didn't
You only
show
show the
it.
control.
There was minimal impact. It improves a bit because I think TI-UGCM is generally quiet period is generally a little positively biased to Saber data. But yeah, I think it's too low to really get huge impact.
And I guess in these experiments, you're not changing the chemistry, right? And the cooling is kind of dependent a lot on the chemistry.
Yeah, I guess I'm not because I guess the only chemistry effects we would have is the, that collision factor, which I don't, this is not, these aren't included in this.
But you're not changing like the neutral. You're not adjusting the neutrals, you're just changing temperature.
Yes. Just it's all temperature impacts, but we are seeing impacts on compositions though, like O to N2 ratio is seeing impact.
And we should probably move on. Is there one more?
Yeah.
So is there anything else about the data itself that could be driving the reduced performance during the more active phase of the storm? Because certainly at low altitudes, there's just phase noise in the data, and I
Yeah.
wouldn't expect you to be able to get much nice out of that. So is there anything like about that high activity time that's making radio occultation data inherently have a higher error bar?
That could be a good point. I haven't looked into that. I guess I'm pretty much removing, like with this quality control that I mentioned, I'm pretty much removing all observations that are just like completely different than what TIE-UGCM produces. Like if it's 50% outlier kind of in the profile, I reject it, but it only produces about 10% of observations. But I think that's a good point too. Yeah, because I guess I attribute it more to the background covariance just because our control and reanalysis are just still so correlated to each other in the nutriency structures we see. So that's why I was thinking that.
Well, thank you, Nick.
Yeah, thank you.
And our final speaker of the session is going to be Hui Xiao, who is approaching the podium now. And she'll introduce kind of